Hey everyone, welcome back to AstroPhobic. Today we're diving into the fascinating world of retrocausality and exploring how the future might influence the past in the vastness of space. So, what exactly is retrocausality? In simple terms, it's the idea that future events can affect past events. It sounds wild, but let's break it down to understand it better. Most of us think of time as a one-way street, from the past through the present and into the future. But in the world of quantum physics, things get a bit more flexible. Retrocausality suggests that this one-way street might have some two-way traffic. Essentially, it means that what happens in the future could potentially influence what has already happened in the past. Quantum mechanics basics. To understand retrocausality, we first need to grasp some basics of quantum mechanics. This field of science deals with the tiniest particles in the universe, like electrons and photons, and how they behave. And trust me, their behavior can be pretty surprising. In the quantum world, particles can act like both particles and waves. This dual nature means they can exist in multiple states at the same time, a concept known as superposition. Imagine flipping a coin and having it land as both heads and tails until you actually look at it. Another mind-blowing concept is entanglement. When particles become entangled, the state of one particle is instantly connected to the state of another, no matter how far apart they are. It's like having a pair of magical dice. If you roll a 6 on one, the other will also show a 6 instantly, even if it's on the other side of the universe. These strange behaviors set the stage for retrocausality. If particles can be in multiple places at once and instantly affect each other over vast distances, it opens up the possibility that events in the future could influence the past. It's a tricky concept, but these basics of quantum mechanics help us get a bit closer to understanding how retrocausality might work. The Double-Slit Experiment. One of the most famous and puzzling experiments in quantum mechanics is the Double-Slit Experiment. It shows us just how strange the quantum world can be and gives us a peek into the possibility of retrocausality. Here's how it works. Imagine you have a light source shining towards a screen with two narrow slits in it. Behind the slits is another screen where we observe the light's behavior. When we don't observe the light passing through the slits, it creates an interference pattern on the back screen, like ripples in water overlapping each other. This pattern suggests that light is behaving like a wave. But when we place detectors at the slits to observe which slit the light particles, or photons, go through, something amazing happens. The interference pattern disappears, and the photons behave like particles, creating two distinct lines on the back screen. It's as if the mere act of observing them changes their behavior. Here's where it gets even more interesting. The decision to observe the particles seems to affect their past behavior. If we decide to observe the particles after they've already passed through the slits, but before they hit the screen, they still act like particles, not waves. It's like the particles knew they were going to be observed and adjusted their behavior accordingly. This experiment suggests that the future act of observation can influence past events. It's a tantalizing hint that retrocausality might be at play. If observing particles changes their behavior retroactively, it opens up the possibility that future events could affect the past in other ways too. Real-world examples. Now let's take these ideas of retrocausality and see how they might apply in real-world scenarios, especially in space. If retrocausality is possible, it could have some incredible implications. Imagine a future space mission. Let's say astronauts are on their way to Mars, and a critical system fails. According to retrocausality, a successful outcome in the future might influence actions in the past. So, a future solution to the problem could somehow prevent the failure from occurring in the first place. It's like having a built-in safety net that reaches back in time. Another example could be cosmic events like gamma-ray bursts or black hole collisions. These events send out signals that we can detect billions of years later. If retrocausality is in play, these signals from the distant future could influence our present understanding of the universe. It's as if the universe is giving us hints about its past by sending messages backward in time. Even in our own history, some scientists speculate that retrocausality might play a role in how scientific breakthroughs happen. Imagine a future discovery influencing the thought process of a researcher in the present, leading them to a breakthrough they might not have achieved otherwise. It adds a fascinating layer to the idea of inspiration and discovery. These examples show just how retrocausality could reshape our understanding of cause and effect. Implications for space exploration. If retrocausality is real, it could change how we approach space exploration in some exciting ways. Let's talk about what this could mean for future missions. First off, mission planning could become a lot more flexible. Imagine being able to receive feedback from future missions and adjust current plans to avoid potential problems. This would mean fewer failures and more successful missions. It's like having a roadmap that constantly updates based on future experiences. During a mission, retrocausality could allow astronauts to make real-time adjustments based on information from the future. For example, if an equipment malfunction is predicted to happen, the crew could take preventive measures before the issue arises. This kind of foresight could make missions much safer and more efficient. It could also revolutionize how we train astronauts. Training programs might incorporate scenarios where trainees receive future insights to handle unexpected challenges. This would prepare them for almost any situation, making them even more adept at handling the unknowns of space. Beyond just missions, retrocausality could impact scientific research in space. Experiments on board spacecraft or space stations could be designed to take advantage of future data, leading to faster discoveries and advancements. This could accelerate our understanding of everything from the origins of the universe to the potential for life on other planets. Of course, there are still many questions and challenges when it comes to proving and applying retrocausality. But the potential benefits for space exploration are huge. Challenges and skepticism. While the idea of retrocausality is fascinating, it's important to acknowledge the challenges and skepticism surrounding it. Not everyone in the scientific community is convinced, and there are good reasons for that. One of the main challenges is the lack of concrete evidence. Most of the support for retrocausality comes from theoretical physics and interpretations of quantum experiments. Without clear, repeatable experiments that show retrocausal effects, it's hard for many scientists to fully embrace the concept. Another issue is the complexity of the mathematics and physics involved. The equations and models that suggest retrocausality are incredibly complex and often difficult to test. This makes it challenging to move from theory to practical demonstration. There's also the problem of interpreting experimental results. Quantum mechanics experiments can be tricky, and results can sometimes be explained in multiple ways. Some scientists argue that what looks like retrocausality could be due to other quantum effects that we don't fully understand yet. Beyond the technical challenges, there are philosophical and ethical questions. If retrocausality were real, it would change our understanding of time, causality, and free will. This opens up a whole new set of debates about the nature of reality and our place in the universe. So, while retrocausality offers exciting possibilities, it's a concept that still faces significant hurdles. The scientific community continues to explore and debate these ideas, pushing the boundaries of what we know about time and space.